We're going to talk about computational thinking for creatives, decoding barriers to entry. Let's get going. A little bit about me before we get started. Tadeh, Hakopian, program manager. I've spent years, educating people about code, educating people about how to learn the basics of thinking of code with computational thinking to get them warmed up. And we'll talk a little bit more about that. But I do not have a coding background from my education. I have an art background in design and architecture, and I learned coding to facilitate the work I was doing in design and architecture. So through my own learning curve and my own experience, built up an ability to translate the kind of knowledge I had to other people. So that's a little bit about me. But today's premise, as a starting point, because the beginning is a very sensitive thing, is at the companies I worked at, we need to teach architects the types of design buildings, like the guy on the right, not the computer architects, how to take advantage of new technology. But they don't know this stuff. So that was a barrier to their entry. They didn't know, and they felt uncomfortable learning it. They were technically savvy, but not the most interested in learning something they weren't familiar with. So how do we make this technical subject matter from another realm that they haven't experienced before, accessible in an intuitive way? What was our way of doing that? Well, we thought about different ways of teaching it, and we knew we couldn't teach it the old-fashioned way. So we wanted to start with not sitting down and giving them some lead code, or sitting down or showing them in a course, but really teaching them the fundamentals of computational thinking. Because this is where architects are working today. This is basically how architects work and think and act today, is through 3D models that are themselves databases. The drawings all come from 3D objects and 3D content that is also enriched with a lot of data. And I do mean a lot of data. So it's like, how do we take advantage of this? Because we're not just making things look good, we're also trying to do analysis, a temperature analysis in a room, make it more comfortable in the room, make it lower energy intensity. We're also trying to do floor plan efficiency routing. So we have a more economical use of our floor plan, but it's also good for people so they don't run into each other. These are the kind of things architects are doing now. So we want to get them to learn, all these designers to learn how to take advantage of these new trends in design thinking. And if I don't start with the approach of how can I make them feel comfortable with this vision of sharing their vision, then coding won't be of much difference to them. So we have to lay the foundations down. The typical design approach for creatives is, okay, you're going to have a couple layers of paper down, you're going to sketch it out with your hand, you're going to have a lot of iterations. It's very touchy-feely, and there's a whole process you learn to do that. It's not just on a whim. There's a whole learning experience that goes into that gets backed up by practical experience. So I wanted to start with the idea of computational thinking as that basis for how we teach people the fundamentals of something like coding and using code to their advantage. And just to kind of give you a sense of the audience of working with these creative types. The audience, like I described, people who like to sketch things out, people who like to really think through in terms of graphics, very visually heavy. They feel comfortable holding things. They feel comfortable with paper, graphics, videos. They're not going to think abstractly in terms of how they're going to, analyze the algorithm or anything like that. They're very smart people, but they're not the kind of people who are going to just sit and really abstractly think something out. They really want to just use their hands to solve problems. And we're trying to teach them something that's, the only thing you're going to use your hand most of the time for is to either type on a keyboard or use a mouse. So that's going to be a bit of a stretch for them. It's going to be hard for them to comprehend that. So for exposure to all this, they're comfortable using computers. Like I said, they are comfortable with the idea of 3D. So they have one toe dipped in the water. But what you don't want to do is start programming right away with code, like text code. They'll freak out, like the fellow on the right here. They're going to freak out and think you're trying to give them like an intense, technical algorithms to solve or something like that. Most of the audience on these calls might be aware that, if you're not accustomed to a command line interface or textual code, it might seem a little intimidating, and that's a lot of people. It might seem too technical, too abstract, too intimidating. How to reduce that anxiety? And you go back to patterns. Buildings themselves have patterns all the time. They have all sorts of different layouts and accommodations, great patterns, bad patterns, anti-patterns, which is where we get all the system patterns. They have the same heritage. Design from buildings, design systems, and computer architecture actually came from the same thinker, Christopher Alexander. Look it up. And so I was like, this is great. This is a great kind of basis to kind of unite these two worlds by a little bit of coincidence. So you can teach people patterns of thinking to help them get comfortable with the idea of how you can really approach something that they're not familiar with. Thinking patterns you can apply to anything, and we're talking about here computational thinking. And all computational thinking is a thought process for expressing solutions as computational steps or algorithm that can be carried out by a computer. That's it. How can you make a very definite finite series of steps that a computer can process, so you're not thinking in terms of big jumps, but really lots of little smaller steps? That's computational thinking. You don't have to be a computer science expert. You don't have to be anything belonging in computer. It's just a computational way of thought process. And here's the key steps in computational thinking: using the abstractions to represent the problem in new and different ways. Sometimes, and we'll see some examples of this, sometimes a problem can be presented in ways you didn't expect, which will help you define the problem better. Some of it's very obvious, some not so obvious. Logically organizing and analyzing the data. How are you presenting the data? Is it in defined sets? Is it something you can break down and analyze? Can you reduce the smaller parts? You want to get to the part where it's as small as you can be without making it too hard to work with. So being able to really deduce. Approaching the problem with programmatic thinking, and that could be iteration, going through different passes, symbolic representation, using values to represent something, logical operators like and or, that kind of thing. And again, you don't have to be working in code to do doing this. Reforming the problem into ordered steps. So after you break everything down and you organize it, can you reformulate the problem into steps of algorithm thinking? And then can you identify and implement solutions with the goal of achieving the most efficient, effective combination? So once we formulate the problem, how do we make it more efficient? And then generalizing. After we go through all these steps, we have a problem-solving system based on the prior steps. Can we then generalize and say, okay, this one base problem can be then used as a general example for multiple problems in the future, that way we can reuse this content. This could be as simple as anything from tying your shoes. You can break that down to smaller parts, from the shoe to the shoelace, the tip of your shoelace to the the part where your foot goes in and all that stuff, to as something as complicated as an entire coding system. And that's how you can prepare people to understand how to abstract problems. You want to break it down to inputs and outputs, data flow, data type, and recursion, so that you can break down all these steps into these essential parts, so they can help them filter through all the steps we talked about prior. And just to kind of give us a boost here, we have some open source tools at our disposal. My favorite, of course, Python, my favorite open source language. And Dynamo, we'll talk a little bit more about that. It's a 3D visualization script, 3D visual scripting software, and Grasshopper, another 3D visual scripting software. These two in the middle are used a lot in the design world. I'll show you their application in more detail. And off to the right is Blender, which a lot of people might know about. It's a general 3D modeling software, totally free. And these are all open source tools. So I always give a shout out to all the open source tools out there. They're completely free, accessible. This is how I got into coding, is a combination of these tools. So always look for the free solutions out there. There's more than a few that you might not realize out there to help you out. And so we want to establish the basis of computational thinking to getting started with these fundamentals. And we want them to feel something comfortable working with in the design world and the build world. And that's going to be something visual, like what you see here. this example of this building that's being built using a lot of the computational design tools, or thinking through tools like Blender. So it's something where it's like, how do we tie the thinking to the project work? And these are the kind of examples we have to work with. It's like, I want to build a building based on, 100 stories, and it has to be a certain shape at the base, a certain shape at the bottom. It has to rotate a certain amount throughout, and that's how do we put that together and make it a facade of glass? These are the kind of things designers challenge themselves to do all the time. You've probably seen them in skyline photos of different cities, and it's not, again, they don't just kind of wing it. There's a whole process they go through to solve this problem. So how do we take something they're familiar with and they've worked on, they can think about, and make it a little more accessible to them in this computational thinking world? How do we take an example like this and develop it? Well, again, we start with the input, process, output, and think it through. And we start with a very straightforward example: how to make a peanut butter and jelly sandwich. We start with something as simple as the key ingredients, the inputs. To make a peanut butter and jelly sandwich, I need peanut, butter, jelly, and bread. And it's like, we take these inputs, like these are the essential ingredients. There's something else I can take into it that could work. But we do have to process the bread. That's the tricky part. You think, okay, the bread's there, but well, if we have a whole loaf of bread, we have to cut it. So that's an operator. You have to divide the bread into 2 equal slices. So we're diagramming this out. This is how we show people, okay, like it's as simple as, okay, what is peanut butter and jelly made out of? If you had to sit down and draw it out into these workflows, how would that work? These diagrams and define it, how would it work? And it's like, well, we have the inputs, we have to process the bread. And then on each side of the bread, we can plug into one piece, the peanut butter, the other piece, jelly. And then we have our sandwich at the end. Something easy to follow. And this is kind of the key thing to this whole discussion, this whole conversation. How do we make this easy for anybody to follow, so that they're not thinking about computer code or software or algorithms or something like that? It's just, okay, like if I were to show you how to make peanut butter, if you show me how to make peanut butter jelly, what are the key steps and how do we process it? And what we like to do is like use these kind of formats you see here, these little boxes everything fits into, where we're plugging in the inputs into another input. So we're processing the bread and we're plugging in the jelly, processing the bread, plugging in peanut butter, so we can see the connections. We can reduce it down to atomized steps, the bread's being sliced. And these are the kind of diagrams that really help people understand the heuristics, the process in a very general format, very non-intimidating, fun. You could do this with anything, cupcakes, how to make a greeting card, whatever, just anything can apply to this. And it's a fun way to really think through problem solving without having to make people feel uncomfortable. It's always the keys. Let's not make anybody feel uncomfortable. So, establish that. So how do we take a little further in our journey with culinary development? Well, after we establish that flow, it's like, how can we take that a little further and make it a little more organized for an actual process? It's using a low coding platform I mentioned earlier called Grasshopper. In this case, all we're going to do is just diagram it, and we're going to do the same thing. How do we make a cup of coffee? Okay, what's my inputs for coffee? You can ask anybody, and they'll say, water, a coffee, and of course a cup. In this case, we say, okay, that's great, but what do we do with the water? Well, in the water, we have to increase the temperature to 110 degrees Celsius. So to put the water and the temperature together into one operator, and the coffee and the cup together into another operator. So this challenges you a little more. There's a few more steps here because you have to remember what you have to process the water. Then once you combine the water and the heat together into, say, a container like a pot, you get the hot water and you get the coffee cup. So you want to make sure you have a specific type of cup, a coffee cup, not just a teacup or a paper cup, a coffee cup, like a mug. And then you're putting the water together into the coffee cup, and you have a coffee cup with water in it. So now the whole point of this is we're taking these finite elements on the left here, we're working right to start putting them together into a format that can actually get us the result of a coffee cup. And all we're doing at the end here is saying, after we start combining these things together into a series of ordered steps that we can define, we can say, okay, we have water in a coffee cup of how much? 12 ounces. So enough that you can drink a coffee in your morning. So that's it. We have coffee. So we're going from left to right with this example of visual thinking. In this case, the only difference between this example and one before it, less visuals in the diagramming part, same kind of diagrammatic workflow. And we have a lot more of a structured approach to it, which will help us in future efforts. So again, we have success here. People can screw around with it. They may not get it the first time, but they're like, okay, I'm just making coffee. Non-intimidating. People can have fun with this. You can use it for 1,000 different examples. This is what I love about computational thinking. You can really apply to just about anything, and the thinking will fall through. Don't take it for granted that you just pour coffee in a cup. What's the elements that go into it? Okay, so we're going to dial it up a notch. Now that I established through these fundamental workflows, how do I apply it to a building? We're not making coffee here, we're making a whole structure. Well, we got this great tool in Plaid here called Dynamo, which is similar to what we've seen before. It's a visual scripting medium that takes the software we're using and these 3D modeling softwares, which have data and geometry, and works with both. So we now can start using real content from real projects to teach them the same thing we were doing with these prior examples. So in this case, this is similar to what we've seen before, visual scripting. And all we have here to work with, as talked to you before, input, process, output, and that's what we saw before in the prior examples. It's just what's your input, what's the processing of those inputs, what's the output. Very finite kind of example here. And the input could be multiple things, in this case, just 2. So simple as, again, make it simple. What's your input? 2 numbers, 1 and 1. Add them up, that's your process. What's your output? 2. You start with this, people are starting, okay, I'm getting it. They could do 2 plus 2, 1 plus 1 on their own to get 2. But we're trying to say, okay, look, if this is simple with these kind of examples, work with me here, and they start understanding, okay, I'm starting to understand and comprehend how this logic works. As the next fun part is working with a little more dynamic information. And this is the benefit of using these kind of platforms. You can really interact with them. In this case, in this low-code environment with geometry, we can see a preview of the work. And it's the same thing. We have inputs, we process it for an output. And what's really great for a designer is they can play around with this. The input on the left here is an element from our geometry. It's what they call a spline curve. It's just a type of line. That's all it is. It's just jargon for line. And an integer slider, seeing how many points along the curve. So they can understand integers like points along the curve. They can understand the model element because they drew it themselves. And they could see in preview here. And they can understand the results they're getting. So all you have to show is like, okay, all we're doing is in the middle, they're processing it. And the magic information is this code block here, which says from beginning to end, just drop points along the line. And you can modify that code block into different text formats, different results. So now that whole touchy-feely kind of point of view of the designer that they love so much working with is available to them in this format. Easy to use, you can add things to it, you can restrict the range of values, you can put only maybe, instead of having like this almost 30, 40 different inputs, you can make it 5, you could change the line type. These kind of things appeal to them. Now, could you do this in a purely code format? Yeah, it's really just an index. There's nothing special about this, but the idea is to teach somebody, again, from a non-coding, non-kind of technical background in this world, how to get comfortable with it. So we establish all that, and we get to more sophisticated examples. So I'll kind of guide everybody through this. On the same concept, same kind of visual scripting, but now we're going to put the whole skyscraper together. It's the fun part. So we have more inputs, same concept, just more inputs. Now that we understand what inputs do and they create points along the curve, how do we then take them and make something useful? Up to now, I've shown you some kind of fun, but not very useful results. They're good for teaching, but not good for project work. So on the left here, we're just trying to create floor plans, literally 4 corners. That's why we have, you have number sliders 30 and 60. Those are giving you coordinates that you can slide around. They could then plug into X, Y, and Z points on 1, 2, 3, 4 points. 4 points can make a floor. It could be 3 for a triangle, but not too many triangle-shaped buildings out there. We're trying to make at least 4 corners. That's why you have 4 point by coordinate boxes. those 4 coordinate boxes will create a floor plan. And when we're going to plug into those 4 points is going to be walls, the levels for those walls, slabs, or a type of floor, and then we're going to process them. Any designer understand the idea of let's use 4 points for a floor and put certain elements like walls and floors onto them. Then we process them. We just go through a process of translating all this. And without going into too much depth here, we're just going to combine the points into one shape. So we're taking those 4 points, processing them, and combine them in one shape. That's the top set of boxes up here called node. And the lower ones, that the actual geometry, we're just going to process them and multiply them by a number of levels. Simple as that. And we are going to then translate them into the output of floors and walls and the output of levels. I'd love to get into more detail about this. I have a whole different take on all this stuff as well, but just follow me here, because all we're doing here is taking the left inputs, processing them, creating outputs. And with that output, we get this awesome thing here. It looks like an accordion or a stack of playing cards kind of falling on top of each other, but that's a floor plan. Those 4 coordinates I was talking about earlier are actually 4 points to a single floor that get populated times 100. So it's only, you can see it down here, those circles represent the first 4 times I ever put those points in, and then I extrapolate it so I have every floor I want in the entire structure. This is just geometry. We can then put it into our 3D software as an entire skyscraper with floors, actual floors, not just geometric wireframe, and actual walls. In this case, they're clear glass, but you can actually see the results. This takes the idea of everything we've seen hitherto of how do you take the inputs, playing around with geometry, using sliders, using points, tying it into something somebody knows, and putting it into an entire structure. This is the computational thinking at work, because I could take this and change it up. I can add more points. I can vary the layout. I can add different materials. And something that becomes, something starts from a very abstract thinking point of view, like numbers and coordinates and points, becomes a real project. So we tie in the finite elements, reduce them, run through some operations of computational thinking into a real project. So this is the kind of thing that sticks with people. And you could take it even further into having just fun with geometry and exploring, again, touchy-feely. So we started from this point of, okay, like, whatever, make peanut butter and jelly and coffee, and now we're at a point where we can play around with geometry, which is something designers love. And from a non-traditional way of showing them how to use computational tools and working with them in a fashion that can facilitate them. Again, how do you reduce barriers to entry? How do you make it easier for people to, from different diverse backgrounds, who are not familiar with coding, who didn't go to computer science degrees, to really get the hang of using these kind of tools to their advantage and not feel like they're left out? Because these kind of tools are becoming more and more relevant. And the more we can take advantage of them, the more sophisticated the results can be for the average person in these projects. And that can be applied for either designers, artists, you name it. So these are the kind of ways we can show people what's possible. And once you get accustomed to working on these real projects, like I just showed you, working on like a skyscraper, I could show anybody how to do that. And how to work with the inputs, how to process them, the outputs, really thinking through these exercises of geometry and planning, you can get results pretty easily. So this is a little more sophisticated result with a similar visual scripting platform. Inputs, process, outputs to get some cool things like this hoop of a building here. So once you get the hang of like, okay, I know that everything's a XYZ point in the 3D environment. I know that I can tie these points together to different ways using these processes. I know that at the end I can get some kind of geometry out of it, and that geometry could be helpful for my project. That's what you need to do, is to tie the thinking to what they're doing and not try to bring them too much, too fast into a world of just plain code. And they get cool results like this. Again, touchy-feely. They love input sliders and moving things around. They could see the kind of like the input to the process to result. And they get these great kind of visuals out of it. And this could be used for a very experimental thought process, building design, you name it. So this is the kind of computational thinking that we use with these kind of low-code platforms, these kind of computational analysis that could be used for anything. In this case, we're using it for the built environment, which I think is pretty cool. But This is a Python conference. I do want to show what's possible with Python here. All this stuff I'm showing up based on decoding, we talk about decoding these barriers and doing the computational thinking. You're trying to get them into the door. We're trying to get them to a threshold where, like, I get it, I understand how inputs work, the processing, I know the value of this, I know I can work with it now. And what they get to eventually is, like, you have these long, big old spaghetti scripts. This one's a little more organized, but they can get pretty intense. So they may want to ask you eventually, like, hey, how do I make this more efficient? And it's like, well, this whole blue area you see here on the left, you can just make it in Python code. And it's the same thing. You import your modules, you do the variables, you write some functions, and you have an output. I cannot start with the things on the right with people I work with because they're just not going to understand any of this. When I started learning this years ago, I struggled because I didn't have a point of reference for any of this stuff. I did come from a CS background myself. But once I understood the basis of all of it in a very structured thinking process and organized that for myself and went through these exercises and got better at them, then I could kind of run with the Python. Then I can run with the code, the actual text code. So that's where you really bring people into this new way of working with code that they didn't say before. And they weren't going to get before because it was so abstract compared to what they were doing. Again, I can't really be touchy-feely with Python code, but I can make your life easier. But I have to kind of bring you into that cult of computational thinking before we can get to let's make your life easier. So that's where we tie into great things like Python. Python's really awesome for just being able to read the code, very easy to follow, very easy to work with. So we could take that and combine it with the visual scripting. And see in this case, I have this awesome little Python script here. Same concept, you import your modules, you put some basis for your variables. And then I have some great coordinates here for a for loop. And that's the for loop of just running through a range from 0 to 100 feet and 20 feet intervals. Again, any designer can follow that. So you have to make it in a format that works and get some cool results, like just laying out some objects in the X, Y, and Z dimension, like I'm stating on the for loop on the left here, into applying properties, applying objects into this mesh, this matrix. And the cool thing here is I can change that range from 1 to 1,000 at 100 feet intervals. I can vary it up. I could do different things with it. So it wouldn't have occurred to me how to do that if I didn't have that internal process of computational thinking of okay, what is the most atomized basic thing? I need to have inputs. Because I'm so used to just drawing things out by hand or modeling them manually, copy. This would have never occurred to me. So you do have to kind of introduce people to this idea of no, you need variables, you need finite variables, and then you need to figure out a way to arrange them in a logical format like a range in Python. And then how do you process them? Can I take this and in the future use as a general problem solving? Yes, that's all possible here. And take it further. It can make some really cool stuff with these combination of using Python with these visual scripts, with that design thinking and computational design approach, or excuse me, computational thinking and design approach for making the models we have on the right here was, like I mentioned in the beginning, architects are trying to do more sophisticated work to make some really expressive designs, more efficient designs that they couldn't do before. So we do have to tie the kind of our own internal experience with the software and tools available. And before we know it, they're creating entire buildings and entire cities using the same approach of inputs, process, and outputs. And how can we bring this down to the most finite possibilities, finite elements, work through a heuristic process, creating operators, making sure everything's organized so that we can get some real structured approaches and back up what you're doing, back up what you're saying as a designer. And make some really cool stuff like, how do we make, 10 different iterations of a tower in a city that facilitate things like sunlight, analysis, and environmental impact, chart it, and say, this is our most efficient building type. This is really the future of where everything's going, not just in the design world. I come from that world, but it's really everything. Whether you're a designer, accountant, a medical professional, you name it, these are the kind of things you want to facilitate to people. And not everybody's going to be able to, go through a CS degree and everybody's going to be able to learn everything about, just computer science, but they can use computational thinking to their advantage. And simple tools like these, nothing's really hard about any of this to their advantage as the world becomes a little more enriched with, computer languages. So the idea is, like, if you want to bring people, if you're trying to train them onto a platform, whether that's pandas or anything else that are becoming more prominent in data, if you're trying to make them feel comfortable with different approaches to solving problems, you have to start with the very root of it, which is how do you get them to think in these terms? A lot of people are very smart, may not be able to think in those terms, and then you lose them quick, and we've all been there. So figure out a way to address that. And before you know, you're coming up with these awesome solutions like we have here of an example of, like, how do you use these computational thinking, again, these giant scripts that are based on the same process, input, process, output, using those defined steps to create something as cool as a automatic floor plan analysis to create the base adjacencies for office layout. How do you do that so people feel great in their office? They're not spending a fortune trying to build it out, and they have lots of space, but at the same time, everybody has a chair, a desk. That kind of thinking is what we're trying to facilitate, and we're not going to do that by teaching somebody Python first. It's teaching them the computational thinking first. And there's also great ways you can apply this to training. I worked for a group that taught people how to do parametric design, computational design, generative design, all the examples we saw before. That's what I worked in the past. So we not only did we have to take these lessons and examples, but also teach them. And we learned that different styles apply to different people. Some people are heavily visual. Design world are very heavily visual, so more graphics and diagrams and pictures, the better. That'll calm them down. Some are cool learning by just listening. Some like to see text examples, read through it. Others like to touch, and sometimes it's a combination. I'm sure there's more than people on this call, on this conference out there, who are like training people at their company or trying to show there's a tool or product. There's lots of different ways to show how something works. So try to learn how people react. The more attention you get from them based on the example you send, whether it's visual or whatever, touchy feel, like I showed those sliders where they can go in and actually touch something even if it is digital. That's how you want to get the feedback. It's like, what is their attraction? What is their rate of response and the rate of engagement? That's how you know it's working. And you may have to vary it up depending on your audience. I had a great team to work with here. It wasn't just me. We had a whole group of people making these tools and trainings available. So that's my team. And we did some great work. Here's some real actual work from the company HMC Architects, where we're trying to get we're helping a designer. Again, we weren't doing this for them. We were helping the designer. How do I make the best, facade for a library? On the one hand, looks great, doesn't look boring. On the other hand, performs, and again, energy results, good energy results, so that people feel comfortable inside, which is what you see on the upper left is an analysis of the facade louvers on this library we have here in the Bay Area. And could you do this manually? Yes. Do we have that kind of time? No. But we did use that computational thinking to our advantage. And we, like I showed you earlier, with this visual low-code scripting medium, we're able to process a lot of different variables in a structured way. A little bit of trial and error, but again, we follow the computational thinking approach of how do we define the inputs, how do we work with what we have, how do we make it into a finite process, order into a series of steps, which is what we did here. And then we get some results, which was this layout on the building on the left here, shows you what these louvers could do. We organized the script so it can vary the louvers in different shapes or different slots, so that no two sets of louvers are the same. We had different panel generations and different results that we could then apply to this building. That on one hand, the designer could control, again, using sliders and modifying the code on their own, but at the same time, it could get you good results, and they could see it with their own eyes. They're not trying to read some command line interface and thinking, okay, that'll give me the results I need. They need to see it. So this is a great example of how we took something that was based on computational thinking, low code, and everything, and put it into a real project that made both the client happy, us happy with the results, and have a great space for people to feel comfortable in while they study in a library. So, key concepts. Let's review everything we talked about. Coding and computational design is more important for the average person these days, because the average person needs to learn more on the nitty-gritty of the code. The out-of-the-box software solutions, even for a pretty comprehensive set of software like what we do in the design world, what we use in the design world, isn't as going to give you the same kind of fulfillment as just creating your own tools, creating your own processes. So we have to get better at that kind of stuff. So we have to think, how do we teach that? How do we facilitate that without having to send somebody through an entire coding program? How do we make that easier for people from non-traditional backgrounds? How do we reduce those barriers, decode that, and make it easy for them? And we want to make them feel comfortable with different, with the compatible training style, and to get comfortable with the concept. In this case, I showed you an example of all those visual scripts, all those low coding platforms, peanut butter, jelly, to coffee, to designing buildings. Compatibility is key. It does take more time, but that is how you get results, so that over time you have a better adoption rate. The computational thinking establishes the baseline of thinking. Again, you can use it for anything as long as you follow the guide for how do we atomize everything, organize it, have a series of rational steps that could be turned into an algorithm for any kind of machine thinking that can apply to anything. Use resources and styles available with your trainees, compatible with your trainees. Like, I didn't show them how to do text coding. I didn't show them how to do something completely unrelated to what they're working on. I showed you earlier, they're trying to make buildings. So let me show you something. Let me work with something that they can make buildings. This example could probably work for just about any profession. There's lots of resources out there. You probably didn't know what Dynamo and Grasshopper and all that stuff was before I showed it to you today. They can be very obscure to one group of people, but very common to another. So go looking for these kind of assets that can help you teach people in their field, whatever it might be. In this case, I'm showing you design in 3D space. It could be completely different for some other people. How to make it compatible with them, so you're not trying to put a square peg in a round hole. Because I've seen that a lot with computer science. It gets kind of challenging to teach people all the time what a difference between a float and an integer is, when all you want to do at the end of the day is just help them out. So think in terms of what they're comfortable with. Reduce anxiety. Start with some easy examples, baby steps. Again, non-traditional backgrounds, but they're trying to learn these tools. So show them the coffee, show them the peanut butter jelly, show them some cool stuff so they get, okay, I get the logic, like input, process, output, and all that. What is the logic? That's what you want to start with, not just immediate coding. Create a structured course. I created a bunch myself to help move along retain knowledge. That way, on the one hand, they can push themselves to learn, but on the other hand, they can retain it so they're not losing it all the time. That could take time. That's a long-term effort, but you start with the basis of meeting them where they are at. Let them try the skills and share the results. Like I showed you some of the project results we had. The more they can feel confident in sharing the results, the better is the advertisement for the process, and the better it is for them to really feel confident. And review, upgrade, continue training forever. Well, I'm talking about training here. This could apply for anything, whether you're learning yourself, teaching others, taking on something new, whatever. It's always a learning process. There's never an end point here. So always be open to new ideas. And can't say it's enough. Support your maintainers, support the Python Foundation. They do great work. Everything here is, I would not have learned what I learned without Python. So shout out to Python, Dynamo, Grasshopper, Blender for being these awesome open source tools. For all the open source supporters out there, I love you guys. If it wasn't for you guys, I would never learn any of this stuff. So shout out to you. Here are some links there, a lot of the different softwares we saw today, and information like pattern language by Christopher Alexander. That's always a great reference guide just to start out with. Dynamo, Grasshopper, all the things you could do with Python, and software like Revit and BIM software that I use day to day. So if you guys are interested in how to make those cool 3D graphics, here's a list. And shout out to the contributors, like I mentioned before, the OSS open source software. They make a lot of great stuff. So shout out to them, shout out to teams that make them as well, and support them all. And here's how you can reach out to me. The QR code is not a Rickroll, I promise. It's just LinkedIn. So let me know if you guys have, if you don't have any questions right now, we'll look at the questions. But always reach out to me if any questions about anything. I'm more than happy to talk with you all. I'm easily reachable through any of these: Twitter, LinkedIn, GitHub, Twitter, LinkedIn, GitHub, and email. You can find me pretty easily on the web. And that's it. If there's any questions, I'll take them.